Okay, this is the 8th video in the linear algebra and modeling sequence. This is called an overdetermined system. So what if I have, we're doing this inverted problem here where we have points and we want to get a line from those points. What if I have more points than I have variables? So for example, here I have 5 points in 2 variables each, so 5 vectors of length 2, and I want a line that's going to fit all of those points. And you should consider that this is often the case in data science. We will most often have more instances than features. So if we call our instances n and our features p, we are generally going to have n greater than p. And when n is greater than p, we call this an overdetermined system. So we've got these 5 points here. Let's go ahead and plot them. And here they are, and you can see that you can see a linear pattern there, and maybe you could eyeball it and draw some line like that. And what we want, so there's no perfect line for these 5 points, but what we want is, we'll call it the best line. We want the best line that's going to go with those 5 points. So I've just gone straight to the matrix notation here. I've taken these 5 points and I've converted them into a matrix where I have a column of ones. And remember, the column of ones is going to go with the y-intercept. We also might call that later on, we'll call that the bias. And then I've got a column of my x values, which are going to go with the beta 1. And then I've got a column of my y values. And you see I just make it by taking each x and putting it into a column, and each y and putting it into a column vector. And we're not going to think of this in terms of all these individual inputs. Part of the reason why I think people hate linear algebra is because they generally are made to work in things like this. And that can be really tedious. It's a lot of bookkeeping. But we're going to be thinking about things like this. We're just going to think about it as x times beta equals y, where this is x, this is beta, and this is y. And that's all we're going to think about. We're going to let R handle all the numbers. So if we want to find beta from this equation, then we could go back to what we've been doing previously, and we could know that beta is going to be equal to x inverse times y. So let's go ahead and solve that with R. So we're going to put in we're going to do this row bind thing again, right? Where each of these is a row vector. And we're going to say y is this column vector here. And we're going to do, let's split this cell. Let's define these first. And then we're going to say that beta is going to be the solution of x and y. We're going to solve this equation with x and y, and that's going to be our beta. And we get an error. Now the error is not super descriptive in R. It just says that a, which is this x here, that's a is a 5 by 2, but it must be square in order for this to work. Now that's one thing that we know about when an inverse exists. In order for an inverse to exist, the matrix must be square. So this is not working because x has no inverse. Now, this is a tricky thing, right? That the meaning of this might be you're not ready for it just yet. Maybe it'll come to you later, or through more study. But we can probably get an intuition for this. The intuition is that there's no line that can match all 5 of these points. There's no one line. Maybe we could do something like draw some sort of like squiggly line that goes through all of them, but we want a single straight line that goes through all 5 of these points, and that doesn't exist. There is no inverse for this. So in the past, I've had students suggest, well, what about a nonlinear solution? Can we define some sort of squiggly line that can go through them all? And yeah, we could. But here's the thing. even a nonlinear solution here, this is a nonlinear equation, right, where we have x squared and x cubed. Even a nonlinear equation, you should look at this and you should say that is a dot product. So even nonlinear equations have linearity built into them. And so it's important for us to develop our intuition and our methods for working with linear equations. So when is there no inverse? The mathematical answer to that question is when the matrix is singular. And this is you maybe never heard that word before in this context. It's a pretty difficult concept, even when you're taking a semester-long course in linear algebra. So basically what it means is we can take this matrix and on some level change it into a square matrix that's got a bunch of columns or rows of zeros. So if you think about a matrix with 5 rows and 2 columns is the same thing as a matrix with 5 rows and 5 columns where 3 of those columns are zeros. So whenever you have a matrix that's got n greater than p or p greater than n, more rows than columns or more columns than rows, then you are going to have either some rows that are all zeros or some columns that are all zeros. And what this means is when you're using the matrix as a transformer to change, you're doing a matrix multiplication to change one matrix into another. If you're multiplying by all zeros, you're going to lose information. You're going to be zeroing values out. And when you try to change it back, you can never recover that information. So you could imagine, like one way I think about doing a transformation where you can't get information back is, what if you had a color image in a matrix and you wanted to change that into black and white? Now, once you've changed it into black and white, you can never change it back into color. You can, do some fancy colorization or everything, but you'll never get the original color information back. You lost that information. You zeroed it out in some way, and you can't get it back. So how are we going to solve this? Well, we've got Dr. Ian Malcolm from Jurassic Park telling us that life finds a way. So what I'm going to do is this fancy process here where I'm going to multiply both sides by the transpose of x. And so what this looks like in terms of the equation is we've got x times beta is equal to y. And I'm going to do the multiplication x transpose x times beta is equal to x transpose y. And I'm not going to solve the first equation. I'm going to solve the second equation. And I'm going to plug that into my solver in R here. And I know for a fact that x transpose x is going to be square and invertible, and I'm going to get a solution to this equation. So let's run it. And let's plot it just as we've done before. And here we have it. There we have generated the line of best fit using this fancy technique. Now, that was really advanced, and I went really fast. But what we basically did there is linear regression. And over the next few weeks, we are going to learn how to apply this in a deeper sense. This is to show you that linear algebra is at the heart of machine learning and data science.